Ever wondered how compilers work? These brilliant software applications act as a bridge between human-created coding languages and the computer's machine code. The intricate process they follow includes several steps, each with a distinct role. The first step involves scanning the code, which results in a series of tokens. These tokens are then parsed and transformed into an intermediate language. This intermediate language is then optimized for performance issues before being transformed into machine code. Finally, the machine code is executed by the computer's processor. Well, you're about to find out. At the heart of every compiler is a scanner, or to use another term, a lexical analyzer. This critical component, a vital cog in the intricate machinery of compiler design, is responsible for a fundamental transformation. It converts raw, unprocessed code into a more comprehensible form that the compiler can operate on more efficiently. This form is known as tokens. Tokens, in essence, are meaningful character strings that represent various elements of the source code. They could be variables, operators, identifiers, keywords, or even constants. The process of tokenization is like translating a foreign language into one the compiler can comprehend. It is this translation that enables the compiler to carry out its primary tasks of analysis and synthesis. Each token gives the compiler a better understanding of what the code is trying to accomplish. That's the beauty of this process. It turns raw code into tokens. Tokens. Imagine a code as a sentence. Now visualize a scanner, not unlike a linguistic savant, breaking this line of code down into smaller units. It meticulously analyzes each part, evaluating for syntactical correctness, ensuring each component is in its rightful place. This scrutiny goes beyond simply reading the code. It considers each part's context, purpose, and interaction with the other parts in an intricate dance of syntax and semantics. It's not just about finding errors, but understanding the syntax's purpose within the bigger picture of the code. This vigilant scanning process is continuous, relentless, and precise. The scanner identifies the role of each word in the sentence. But how do we build such a sophisticated scanner? The answer lies in our ability to utilize highly effective tools that are readily available to us. One such tool, known prominently for its proven efficiency and reliability, is yacc. Yacc is not just any tool. It is a powerful program designed with the specific intention of generating lexical analyzers. Over the years, it has gained a reputation for its ability to create these analyzers with precision, leading to more accurate results. It's a versatile tool, capable of handling diverse scanning needs, making it a favorite among developers. It simplifies complex processes, improving both productivity and quality. It is a tool that truly personifies the advancement of technology in our time. yacc, a program that generates lexical analyzers. Firstly, understanding the syntax of yacc is crucial. Yacc is a computer program that generates lexical analyzers, and in order to use it effectively, we must comprehend its structure. The interesting fact about yacc is that it isn't a standalone program but is used in conjunction with other programming languages. Delving deeper, the structure of a yacc program is inherently threefold, meaning it comprises three distinct sections. Each section has its unique function and importance. The first section contains definitions, the cornerstone of the program. They define the set of regular expressions to be used in the program. Following the definitions, we have rules. These rules set forth the actions that must be taken when the definitions are met. They are an integral part of the yacc program as they dictate how the program responds to different inputs. The last section contains user subroutines, a set of instructions that specify what action is to be performed when certain conditions are met. It's the final piece of the puzzle that brings everything together in a cohesive manner. The definition section is where we declare variables and import headers. This area is the backbone of any programming project, serving as the vital control room, the grand central station, so to speak. It's a storage area that's brimming with all the necessary components that make your code function correctly. Just as a pantry in a kitchen holds the most crucial ingredients for a chef, so too does the definitions section hold the most critical elements for a coder. It's a space where vital components such as variables, headers, and other key ingredients are held ready for use, a place where the magic of coding begins. It's a place where your code's building blocks are stored, each item with a distinct purpose and a role to perform in the grand scheme of your program. It serves as the starting point where everything needed to build and maintain your program is stored. It's a storage area for essential components. It's like the pantry of a kitchen where we store all the ingredients we'll need. Our next stop on this splendid journey is the Distinguished Rules section. This, ladies and gentlemen, is the heartbeat of our operation, the very stage where all the magic unfurls. Within this realm, we, like skilled artisans, meticulously create our guiding principles. These principles, these rules, they follow a particular structure, a significant pattern, a recurring pattern action formula. This structure isn't random, it's quite akin to a well-orchestrated recipe. A recipe that provides explicit instructions dictating the fate of our ingredients. So as we delve deeper into the intricacies, it's like a recipe telling us exactly how to handle our... Finally, we have the user subroutines section. It's an optional section of our program that focuses on storing functions that are not essential, but could provide additional features and enhanced functionality. It's like an auxiliary toolshed, a place where we can keep bonus functions that we may find useful as we continue to develop our program. Here, we can store routines that we might need in the future, routines that aren't necessarily critical to our program's basic operations, but could prove advantageous down the line. This area could include routines we might require. Now, let's get into the nitty-gritty of developing a scanner. This technological expedition promises a thrill that tech enthusiasts crave. Our voyage into the realm of technology is not just about creating a scanning tool, it's an endeavor to explore, to understand, and to dissect the complexities embedded within the process. Each phase comes with its own set of challenges, mysteries to unravel, and lessons to learn. We aim to break down these aspects, demystifying the process step by step, shedding light on each crucial component to make the journey more comprehensible and engaging. We won't leave any stone unturned. Our exploration will dive deep into the intricate layers of the development process. By embarking on this technological voyage, we aim to build not just a scanner, but a scanner that is proficient, efficient, and precise. A scanner that is capable of effortlessly identifying different token types in a C program. Our scanner will be adept at identifying token types in a C program. We start by defining the token types in the definitions section. Tokens are the smallest meaningful units of a programming language. They act like building blocks, paving the way for any programming language to communicate instructions to a computer. Tokens are classified into different categories, each with its own unique characteristics and functionalities. Some of the common types of tokens include keywords, which offer predefined instructions or actions in a language, identifiers, that name entities like variables and functions, operators, which perform specific operations between operands, and delimiters, that separate different parts of a statement or program. Understanding these elements is fundamental to programming and scripting languages. Tokens such as keywords, identifiers, operators, and delimiters are examples. After laying the groundwork with definitions, we venture into the crucial segment known as the rules section. Within this section lies the essence of our operation, where each token type is assigned a specific rule, tailored to its unique characteristics. This process of formulating rules isn't arbitrary, but meticulously thought out, ensuring precision and effectiveness. We delve into the intricacies of each token, studying its nature, before crafting a rule that corresponds seamlessly to its identity. An illustration of this process is the rule for an identifier. This rule stipulates that an identifier could be a series of alphanumeric characters, each initiated by. Once we've defined rules for all our tokens, we can run our yacc program. Yacc is a tool that uses our specified rules and definitions to create a C program. This efficient program, when compiled and executed, can expertly analyze the given input code. This might sound complicated, but don't worry. It's like learning a language. It eases with practice. Appreciating a scanner's workings reveals compiler's complexity and elegance. In summary, we've learned what a scanner or lexical analyzer is and how it forms the phase of a compiler. Essentially, it's a program that translates code into tokens to be interpreted. So the next time you hit compile, spare a thought for the humble scanner, working tirelessly behind the scenes to make sense of your code.